1022.
Doctor,
Yes.
we have a quiz on Wednesday, right?
Tomorrow, yes.
What is the material?
It's actually, I've been repeating this all over each slide. Okay. So let me just point this out. Okay. طيب. Bismillahirrahmanirrahim. Welcome to E201. So today's lecture will be our 12th lecture, and in today's lecture we're going to cover the we're going to continue talking about what we've covered in the previous class. So if you remember, we started talking about source transformation, and in this lecture we're going to continue talking about source transformation and introduce the notion of Thevenin and Norton equivalent circuit. Before we start, there are a few announcements. So there's one announcement actually. We have quiz 2, which is inshallah tomorrow. Going to be tomorrow inshallah during class time. It's going to be the exact. We're going to have exactly the same instructions as the previous quiz. So make sure that you refer to these instructions. As far as the material, it's going to be 3.1 to 4.4. What I mean by 3.1 to 4.4, I mean anything from 3.1 to 4.4 that's part of the syllabus. So this excludes 3.5, 3.6, I think 3.7. The remaining part of this will only include the first 4 sections of chapter 3, which is 3.1, 3.2, 3.3, 3.4. So when I said like things that are part of the syllabus, when I say like 3.1 to 4.4, I mean that anything that's part of the syllabus. Is it clear?
Yes, thank you.
Okay.
Yes.
Okay. So we always have the syllabus. So I'm not going to give you anything that's outside the syllabus. So just keep this in mind. I'm not going to give you anything that's outside the syllabus. Everything that I'm going to ask you about will be within the syllabus. If this section is part of the syllabus, yes, then we are going to. It's going to be part of the quiz and exams, of course. If it's not part of the syllabus, then I'm not going to give you anything extra. Okay. So just going over. Hold on a second. So just going over what we did last time. So if you recall, we studied starting at the beginning of chapter 4. We were concerned about developing a systematic way of solving circuits. So we have a very complicated circuit, and we said, well, let's find a mathematical simplification, a mathematical way of constructing a solution in an easier manner that's not going to involve inverting a high-dimensional matrix. And we realized that, well, we can do that by introducing intermediate variables. So we started with the node voltage. So we said, like, instead of solving directly for the essential branch currents, let's solve for the essential node voltage, and using the knowledge that we obtained after solving the node voltage, after solving the essential node voltages, we can find the essential branch currents. So that's the method. That's the first method that we use. It's called the node voltage method. The other method is like, well, instead of actually solving for the essential branch currents, let's solve for the mesh current. And we said, like, in most cases, the mesh current is a fictitious current. It doesn't exist, but it's kind of like an intermediate way that's gonna give us a rather simple way of solving complicated circuits. Then we studied the difference between these methods and which method to use, and we realized that it all depends on the problem itself. unless you are asked explicitly to use a specific method. So these we said like these two methods, they were attempting to when we applied them, we were attempting to solve the circuit as it is. So we're not trying to simplify the circuit itself. We're trying to simplify the mathematics of solving the circuit, but not the circuit itself. Then in the last lecture, we introduced a method to simplify the circuit itself. It's called source transformation. We saw that oftentimes we have a series current, a series voltage source, a voltage source in series with the resistor, or a current source in parallel with the resistor, and we said that, well, we can move between these two representations, provided that the current and the voltage are related by this equation. Okay, so we studied the simplified version, and let's talk about a more like a special case of source transformation. So let's consider what happens in this situation. So what do we care about here? We care about having the same current here, supplying the same current here, and supplying the same current here, with or without. Okay, we care about supplying the same current. So let's say that we have a voltage source in parallel with the resistor. In this case, the voltage across the resistor here will be exactly the same as the voltage source because they are in parallel. So if they are in parallel, they share the same voltage. Says that, well, we can actually remove this resistor, and this removal will not change the current here. If this is Ix, then this is going to be Ix with or without the parallel resistance. So you may say, why do we have, what impact does this resistor going to do? It's actually going to affect the total current supplied by the source. But if we're interested in solving, like the power generated by the source, then we should keep this resistor. If we're interested in finding the voltage or the current at any part of the circuit, then we can remove this one, and this will not affect the transformation. Note that if we go back here, you can start from this representation then to that representation, or you can, if you want to go back, you're going to go back exactly to the same representation. So there is a one-to-one relation between them. However, here, if I give you this representation, then you can easily move here. Just remove the parallel resistor. Now, if I give you the parallel resistor, then you will have infinite possible. If I give you this representation, and I told you that this is we have a voltage source in parallel with a resistor, and you would say like, well, I have infinite possible choices of the parallel resistor. I can only constrain this if I know the power generated by the source, the needed power generated by the source. So the backward transformation is not unique. We can do the same if we have a current source in series with the resistor here. So if we remove the resistor, then the current here, if I call it IY, will be exactly the same as IY. So imagine that we have a fictitious load here. And here, it's going to be exactly the same load. So the current supplied to that load is going to be exactly the same in both representations. Is it clear, Shabab? Any question?
دكتور ممكن تعيد شوي ما فهمت عادل.
Okay. So what happens here, if you have a parallel voltage source, if you have a voltage source in parallel with a resistor, And say like you want to connect a load here. Let me call this one RF. And you want to connect the load here. It's exactly the same value. Okay, you're following?
Yes, I am.
Okay. So the question is, will IX be different or will it be the same?
Will what?
Will IX, the current supplied to the load, will
No,
be different?
No, it will be the same.
It will be the same. So having this parallel resistor does not affect the load supplied to, does not affect the current supplied to the resistor. So the reason for that is you can imagine you have a fictitious voltage source here, and this one is Vs. Okay?
Okay.
We can do the same here if we have a current source in series with a resistor. So if you connect a load here and the same load here, and I'm asking you to find IY, you'll see that having a series resistor over there does not affect the current supplied, does not affect the current passed through IL.
Yes, it is.
So we can remove it. Umar?
Okay, thanks.
Umar, Saleh?
Yes, Doctor, I didn't get how the parallel resistor does not affect the current.
It does not affect the current supplied to the load. Okay?
I still didn't get
It will not affect the current. Let's prove it here. Let's see if we can. If I ask you to find the current supplied to this load, then you would say by Ohm's law, by KVL. Let's think about this situation. By KVL, let's say that the voltage across the parallel resistor will be Vs, صح? Plus Ix RL equals to 0. So Vs, or let me say that, Ix will be Vs divided by RL, صح? You're following?
Yes.
Okay.
Yeah.
Now if I go to the same circuit here, if we go to the other circuit here, and I'm trying to find the current Ix here. Again, I'm going to apply Vs plus IXRL equals to 0. So Ix will be Vs divided by RL. Okay? واضحة؟ عمر.
Yes, thank you.
Okay. عبد الإله.
طيب دكتور ليش ما استخدمت الار في الكي في ال هذه؟
This one?
ايوه الار الار
This
اللي
one?
في السيركت.
This one? The KVL here?
ايوه في ار في السيركت ما حطيته في الكي في ال.
Okay. So remember when I apply KVL, what do I care about?
الاشياء اللي باللوب.
The voltage, right?
The voltage.
So what's the voltage across RB?
مو قصدي ار بي قصدي الار اللي فوق.
R. Yes, you can add R here. And similarly here, IXR, in this case plus R, in this case plus R. Okay, you see that the current is exactly the same, صح? You see that the current is exactly the same.
ايه.
Okay, good. So we can do the same here if we apply if you apply if you apply KCL here in this circuit, you can get the same current. In this representation, it's going to be exactly the same as KCL in this representation. What matters here, شو اسمك عمر, is if you're trying to measure the fault, if you're trying to find the power of the voltage source, let me call this one IS. IS multiplied, or negative IS multiplied by VS. صح? So this is
Yes.
okay. In this case, what is IS in this circuit? Let me call it A. IS will be the summation of, say, like VS divided by RP plus IX. صح?
Yes.
Okay. What about in circuit B? IS will be IX. So you see there is a difference. There is a difference in current. So the power is not going to be exactly the same. So if you want to calculate the power, then you should go back to the original circuit. You cannot use the simplification. But if you care about the voltage or the current, you can use the simplified version. We'll illustrate this with an exercise. So let's apply the source transformation to find V0. So we have V0 here. Let's try to apply source transformation to find V0. So what do we notice here? Well, we notice that we have 250 volts, 250 volts in parallel with 125, and we have 25 ohms. So what will be the first simplification? Let's start with Walid.
Yes, we can remove the 125 resistor.
Okay, let's.
And 10.
Okay, exactly. So we can remove the 125, this one, and the 10 ohm resistor, because 125 is in parallel with the voltage source. 10 is in series with a current source. So we can remove them and get like the very first step of the simplified circuit. So let's do that. So 25. Because here I removed the 125, so I will get the 8. Yes. Okay, so we can remove the 125 and the 10 ohm resistor, and we get this simplified circuit. Then what will be the next step? Let's see, Wael.
Yes, we can introduce a new current source.
Okay, so we can transfer the 250 applied source transformation for the 250 ohm, 250 volt with the 20
to 10 ampere current. Okay.
Okay, we can what?
We can introduce a new current source.
Okay, so what we need to do is something like this. Okay, so now what do I have? I have a current source, two current sources. They are in parallel, so I can add them up. And let's see, Ibrahim, what will be the next simplification?
After we add the current sources together, what we need is the V naught across the 100 ohm resistor.
Okay.
Which will be the same across the three resistor we have here. So we can combine them as one equivalent resistance.
Okay, exactly. Or what I will do is something different here. I can combine them, but I decided not. So what I did here, so I added the current sources. So we have 10 ampere going up, 8 ampere going down. So I added them. So it's going to be 2 amperes going up. And instead of actually, what you said is actually correct, but I want to make sure that you guys memorize or remember the
current divider.
Current divider, yes. So if I apply the current divider here, what should I get? R equivalent. So the current divider here is going to be R equivalent divided by 100 ohms multiplied by 2. And the equivalent resistance is 10 divided by 100 multiplied by 2. And this is going to give me 0.2 amperes. So now I have 0.2 amperes. So V naught will be 0.2 multiplied by the resistance, which is 100, and this is going to give me 20 volts. So V naught is 120 volts. Okay. Now, let's find the power developed by the 250 voltage source. So this is the second thing that we need to do. We have to find the power developed by the 250 voltage source. So in this case, we need to go back to the original equation, the original circuit. So if we go back to the original circuit here, copy it. If we want to find the power developed here, what should we do, Ahmed? مو أحمد شو اسمه زياد.
We find that it is 2 ampere as a current source. So we do passive sign convention and multiply I by V.
So what is the current here?
2.
Why 2?
Because we found it previously.
Not really. طيب حسن صاير؟
دكتور بتحاول تتخلص من كل شيء إلا 250 volts.
Not really. There is a shortcut. Let's see. Yasser?
Yes, the current in the 250 voltage source is the current in the 125 resistor plus the current in 25 resistor.
Exactly. So what is the current and
And the 125, it is 250 over 125. And the current in the 25 is, we're gonna apply KVL on the big loop. We know the voltage. We can apply KVL from 250, 25, and across the 100. So it is gonna be 250 minus 20 over 25.
Exactly. Oh, actually applying Ohm's law.
Yeah.
So I1 will be Vs, which is 250 divided by 125, and this is going to give us 2 amperes. I2 will be 250 minus the voltage that we found, which is 20, divided by 25, and this is going to give us 9.2 amperes. So the total current will be the summation of both currents, so it's going to be 11.2 amperes. So you see here that the parallel resistor contributed to the current supplied by the load. So now we know the current, so we can easily find the power. So what's the power? In this case is 250 volts. So using passive sign convention, it's going to be 11.2 multiplied by 250, and this is gonna give me minus 2800 watts. Okay, very good. So now we want to find the power developed by the 8 ampere current source. Omar, question?
Yes, doctor. Quick question, please.
Yes.
Why did we subtract 250 minus 20? I mean, sorry, not why. How?
How? Because we measure the voltage from the previous step. We said that the voltage V0 is 250, is 20, صح? So the
Yeah,
voltage
okay.
here is 20 volts.
Okay.
So if you apply Ohm's law, you're trying to find I2.
Oh, yeah.
Will be 250 minus
Yeah.
20. Okay.
Yeah, thank you.
Good. Okay, the third part is asking us to find the power developed by the 8 ampere resistor, 8 ohm current source. So in this case, what I will do, I will take only this portion of the circuit. So if I take this portion of the circuit and try to redraw it, it's going to be something like this. So I know this one. I know this is V0, which is 100 volt. This is not 100 volt, 20 volt, which is something I did calculate in the first step. So what I need to do is I need to find the voltage across the voltage source, across the current source. So applying KVL, this is going to give me minus 10 multiplied by the current source, which is in this case 8, plus V1, which is the voltage across the current source, plus 20 equals to 0. So in this case, V1 will be 60 volts. So the power developed by the 8 ampere source is going to be minus 8 multiplied by 60, and this is going to give me 48 watts. So remember, both sources actually deliver. Okay, it's clear, Shabab? So when I do the power calculations, I need to go back and keep those resistors, the one in parallel with the voltage source and the one in series with the current source. If I want to do the voltage or the current calculations, I can keep them or leave them. It's up to me. But if I leave them, I will get a simplified version. Talal, question?
No, not a question. I think you missed a 0 here in the power.
Oh,
60
okay.
divided by 8.
For 8, yes. Okay, thank you. Good. Okay. So let's take another exercise here and see what happens. And this is kind of some sort of like a standard way of applying the source transformation technique. So we have the following circuit, and in the following circuit, we see that we have a voltage. We have 3 sources actually, and we want to apply series of voltage, series of source transformation to get I naught. So what is I naught? I naught is the current here. So we're going to apply source transformation to get a simplified version or a simplified version of the circuit. So the very first step that I want to emphasize here, if I ask you to find I naught, you should avoid doing anything with this part of the circuit. So just keep this part as it is. Try to work on the parts that are not related to this part. So let's just start with Mohammed al-Sweden.
Yes. We can merge the current source with the resistor. So it will be a voltage source.
Which one?
On the left. Any one of them would work, but I meant the one on the left.
Okay, so let's do more than one step at once.
Okay, let's what?
Do more than one step at once.
So we will have to put a voltage source here, which would be 6/2, 3.
It will be 6 multiplied by 2.
6 multiplied by 2. It will be 12 volts. The one on the left.
Okay.
And the one, the upper one would be 5 multiplied by 1.
Okay, good. Salman, what else? Salman.
Yes.
What else?
Then we can combine the resistors. There will be in series.
I think one is
After
missing.
making the voltage source with the 6 ohm resistor in series, it will be 6 ohm and the 6 ohm and the 5 ohm. All of them will be in series. We can combine them.
Okay. The Kareem, what do you think?
What I want to do is subtract voltage.
Okay, I think, okay, good. I think we're going to keep repeating the same thing here. So, Shabab, what about this one? Why did you ignore it?
I wanted to subtract it from the new voltage.
You cannot. You see what? You cannot do that because it's not going to be in series. You have this branch. Okay, so let me redraw the circuit. Let me get this one. So this is by applying source transformation here. We have 12, 6, and there will be another 6 ohm resistor here. Then we apply source transformation here. So we have a current source in parallel with the 5 ohm. So it's going to be 5 ohm resistor. And remember the direction of the voltage source. It should follow the direction of the current. Then here I have a 17 ohm resistor in series with the voltage source. So I can convert it into a resistor in parallel with a current source. And because of the polarity, the current source is pointing down. And this one going to be 2. And then we lastly have the 1.5 ohm that we trying to find the current passing through it. So now we can do a series of simplifications. So we can see that we have, this one is 5 volts. We see that 5 and 12, they are in series, so I can combine them. So I will get 17. And I get 6 plus 6 plus 5, which is 17 ohm. 17 ohm here. Okay, Mahsen, what will be the next step?
دكتور عندي سؤال بس.
كيف؟
عندي سؤال.
يس.
الآن 17 اوم ريزيستر والكرنت سورس لو بدلت الأماكن هل بيصير بالحل ولا لا؟
This one?
Yeah.
It shouldn't matter. They are in parallel.
Okay. Thank you.
Okay. So now I convert this 17 ohm voltage source to a current source in parallel with the 17 ohm resistor. So it's going to be 17, another 17. So now it can be easily solved by noticing the following. You have 17 ohm in parallel with 17. So this is going to give you 8.5 amperes. So 2 resistors parallel. You have 2 current sources. They are in parallel, so you can add them up. So the result will be something like this. And this one is going to be 1 ampere. So remember, you're asked to find I naught, which is this current. So if you apply the current divider law, you should get I naught negative, because remember the current divider law will give you this current, this polarity, and this current, and this polarity in terms of this current. So I naught will be the negative of this one. So it's going to be 8.5 divided by 10 multiplied by 1, and I naught will be negative 0.85 amperes. Okay. The second part is asking to verify it using node voltage method. So you can, at this stage, finding or applying the node voltage method will not be that complicated. So you need to specify the essential nodes. So according to what we know about the node voltage method, this could be the reference node. This could be V1. V2, and V3. So once you find a V3, you notice that I naught will be V3 divided by 1.5. Okay. So now let's move on to a new topic. This topic is something very interesting and very important, and you're going to use it not only for this course, but probably for most of the courses in electrical engineering without knowing that you're actually using it. So this one is called Thevenin and Norton equivalent circuits. And let me start by introducing the notion of Thevenin equivalent circuits. So if you want to connect like a toaster to the power outlet, what do you care about? You care about, say, like, or any device. You care about the power rating. You care about the voltage, and that's it. You don't care about the internal circuit inside that device. So this is not important to you. So most of the applications, you don't care about what's going on inside of the circuit. So what we want to do is actually find a way to represent a very complicated circuit using a simplified version. So this simplified version, voltage source, a resistor, voltage or current source, a resistor, and this is going to give you the enough representation that you need to use for specific applications. So therefore, this is very useful if you want to connect cascade circuits. So you want to connect this circuit. That circuit is going to give you, say, like, filter some of the noise in the speech signal that you're trying to process. Then next to it, you will get a circuit that's going to magnify that voice or that sound that you receive. So you have multiple circuits. You want to connect them all together. And this is very important. It's very important that most of the time you don't care about what's going on inside of these. So you will buy a specific IC from the market that's going to give you the amplification. But what you care about is the voltage and the resistance of those. So you can design the remaining part of your system according to the specification that's given to you. So it turns out there is a nice approach, a nice configuration called Thevenin and Norton equivalent circuit that captures the essence of the parts of the circuit that you are interested in. So let's think about it this way. So you have a resistive network containing independent and dependent sources. And you decided to say, like, well, this is the first point of connection. This is the second point of connection. So I'm gonna bring a wire here, and connect another device here. And you may ask yourself, what do I need from this complicated circuit? I don't need to know exactly what's going inside. I need something that captures the essence of the circuit. So I need a voltage source in series with a resistance. And this is called, the voltage source here is called the Thevenin equivalent voltage. And the resistance here is Thevenin equivalent resistance. So is this configuration or this motivation, is it clear for you, Shabab, before we proceed?
I did not get it, Doctor. I'm sorry.
Okay.
I did not get it.
Okay. So imagine that you want to connect, how to say it? imagine you have okay. If you have a device and you want to connect it to the outlet, the power outlet, okay, do you care about what's going on from the power plant to the to your home, or do you care about the voltage of the power outlet and the amount of the current that can handle?
Only the power outlet.
What's that?
Only the power outlet.
Yeah, you care about the outlet, the voltage, and the power that can handle. You don't care about what's going on from the power plant, from the generation until transmission, until being delivered to your home. So this is, you don't care about. So what you say that, well, I can represent the entire system from the power generation to the power outlet using a voltage source in series with the resistor, and then you connect your device. Is it clear now?
Yes. Thank you.
Okay. So what we want to do, what we want to study, we want to study this representation. How to build this representation if we have a complicated circuit. Ziad?
Is it only this representation and cannot be a current source with a resistor in parallel?
Yes, because that's why we studied actually source transformation before. Because we know that we can start from one and go to the other. So if you recall, in the beginning of this lecture and the previous lecture, we showed that we can use source transformation to move between a voltage source and a series of the resistor to a current source in parallel with the resistor. And this will guarantee the same Ix here. It's going to be exactly the same. So the relation between I short circuit here, this one is called V Thevenin, this one is called R Thevenin, and the current source is called I short circuit for a reason that will become clear in a moment. They are related by Ohm's law. So V Thevenin equals to R Thevenin multiplied by I short circuit. Okay. So this is the representation. But now, if we are giving a circuit that consists of a voltage source, consists of sources and resistors, how to find the Thevenin equivalent circuit? How to simplify, say, this circuit into something, or for example here. So what we did actually, if you recall, we simplified the entire circuit. We simplified the entire circuit from here to there by the following. So this is exactly what we did. So we have this big, huge circuit, and we simplify it using the following simplification. So the 1.5 ohm resistor here is actually seeing a current source in parallel with the 8.5 ohm resistor. Or if you want to apply the source transformation, the current source, the 1.5 ohm, is seeing 8.5 volts in series with the 8.5 ohm resistor. Is this clear, Shabab? Hadi?
So, Doctor, we need just to find the output, and then according to the output, we need to make the circuits, right?
You need to find the output. What output?
Output depends on the circuits, A and B.
Yeah, you need to find the representation that if you decide, okay, this is going to be, in this case, if I assume that this one will be my load, then this is the circuit that, say, like generates, this is the circuit that creates a voltage source or a power source of my load. So I'm going to connect my circuit here, my load here, to the power generating circuit here. We'll come to it. We'll see how to apply it, and this will actually clarify most of the ambiguous, most of the things that we're not clear. So you may ask yourself how to find the Thevenin and Norton equivalent circuit. So there are multiple cases. The first one is you start with, well, do I have dependent sources? If the answer is no, so let's see how to find it. So let's imagine we have this complicated circuit, and inside this circuit we have the following. We have a bunch of resistors. We have voltage sources. We have current sources. Of course, those are connected to one another, but I'm just specifying the things that are inside. And you want to take the output of your circuit between A and B. So imagine that this is a circuit that takes 120 volt voltage source voltage and convert it to 5 volts. And here you see that, say, like this is the 5 volt output. So what should you do? So the first thing is, if this is your device and you can represent your device with a load. So what should you do? The first thing is you need to, if you want to find the Thevenin, if you want to find the simple representation of this circuit, so the first thing you need to do is disconnect this load. Then if you disconnect it, you need to find the open circuit voltage here. Okay, you take this one. You remove the load. And you try to measure the voltage here. This is the open circuit voltage. The open circuit voltage, which is equal to beta. So this is the first step. The second step is you need to connect the two terminals, A and B, and measure the current here. And this current is called the short circuit current. So if I take this one here, I take it here, copy it, use. So you connect these two terminals and you measure the short circuit current. So now you have the voltage and you have the you have the open circuit voltage, you have the short circuit current. So now you need to take the ratio of these to get the Thevenin and resistance. So if you take the ratio, our Thevenin will be V Thevenin divided by I short circuit. So now you find the representation. So you find the Thevenin voltage, you find the Thevenin resistance. It turns out there is another way. If you have independent sources, you can actually deactivate all independent sources and find the equivalent resistance between the two terminals. So if you want to deactivate the sources, you mean you want to zero these sources, you want to remove the contribution of these sources. So if you have a voltage source, the voltage source is supplying constant voltage. So if you want to zero that, you want to change the voltage source to a short circuit. Why? Because the voltage across a voltage source is zero. If you want to deactivate a current source, you want to zero this the contribution of this current source. So you want to replace it with open circuit because the current passing through an open circuit is zero. Okay? So let's illustrate it with an exercise. So we have the following circuit. In our case here, it's disconnected. So the load is supposed to be connected here. So the first part about disconnecting the load is not there anymore because the load is disconnected. So let's find the Thevenin equivalent circuit with respect to the terminals A and B. So basically what I need to do is I need to find the values of this circuit. What is V Thevenin? What is R Thevenin? So let me start with V Thevenin. So for this circuit, what I can do is I can use any technique that we studied to find the voltage A and B, the voltage VAB, which is this voltage. So clearly this one calls for, if we want to do it with node voltage method, this will be easy because I know this one. This is 72. The only thing that's missing is this one, V1, and this one is V Thevenin actually. So one of the node voltages is actually the Thevenin voltage. So let's apply the node voltage method. So if I apply the node voltage method, then by this time I think we mastered the node voltage method. So it's going to be V1 divided by 20 plus V1 minus 72 divided by 5 plus V1 minus V Thevenin divided by 8 equals to 0. And if I group the coefficients, so I'm going to get 1 over 5 plus 1 over 8 plus 1 over 20 multiplied by V1 plus 1 minus 1 over 8 V Thevenin. So this is the first equation. The second equation is applying the node voltage at V Thevenin. So it's going to be V Thevenin minus 72 divided by 12 plus Thevenin minus V1 divided by 8 equals to 0. So if I simplify it, so this is the second equation. So I have two equations, two unknowns. So I can easily solve for that. So V1 will be 60 volts. Thevenin will be 64.8 volts. So now I found the first part, Thevenin. So the second thing is I need to find Thevenin. So to find Thevenin, I can find a short circuit. I can connect these A and B together and find the I short circuit. Or since I have independent sources, so I can simply deactivate the sources and find the equivalent resistance between A and B. So I will use the second approach because it's easier and it's faster. But if you want to verify it, you can use the find the I short circuit current first, and then from that you can find take the ratio and find the R. So you see here I deactivated the 72 voltage source. So by replacing it with a short circuit. Okay, so now what is the equivalent resistance here? So I have 20 ohm in parallel with 5. So this is going to give me 4 ohm. Then I will have 4 ohm in series with 8 ohm. And this series combination will be in parallel with 12 ohm. So I will have 12 ohm in parallel with 12 ohm. And this is going to give me 6 ohm. So it turns out this circuit can be represented as the Thevenin equivalent circuit between A and B is going to be a voltage source in series with 6 ohm resistor. Okay. So let's try to find the Norton equivalent circuit here. Yes, a question?
Yes, doctor. The deactivation method also works on current sources?
Yes.
Or all inputs? Okay.
It works on both. We go back here. If you deactivate the voltage source, then you're going to replace it with a short circuit. So in this case, the voltage, of course, if you want to deactivate, you want to make sure that the voltage source is 0.
Yeah.
Okay.
Thank you.
The current source is replaced by an open circuit, and this guarantees that the current is 0. Okay. So let's try to solve this exercise. Okay, it asks us to find the Norton equivalent circuits between terminals A and B for the circuit shown below. So we have two approaches. The first one is actually to find directly the Norton equivalent circuit, meaning that you need to find the short circuit current first. The second approach is you find the Thevenin equivalent circuit, then you apply source transformation to get the Norton equivalent circuit. But let's use the first approach. So maybe this circuit looks compact when we see it here. But if we want to solve it, maybe we need to do a little bit of redrawing. So let me redraw the circuit. So if I do that, okay, this one looks easier to solve. If I ask you to find the short circuit current between A and B, what should you do? Shabab, if I ask you to find the short circuit current between A and B, what should you do? Anyone? Okay. Why everybody's scared? Okay. Hadi.
Can I use the current divider?
Yes, you can use the current divider, but you need to make one specific simplification. So if you want to find the short circuit current, what you need to do is first is you need to connect a short circuit between A and B. What implication does this current or does this connection has in the circuit? This is going to change the circuit. Because we're going to have a short circuit in parallel with the resistor. So what's the equivalent resistance here? Shabab, we have a quiz tomorrow. And this is part of the quiz. So it's going to be a short circuit. If you have a short circuit in parallel with the with the resistor, then the equivalent resistance is 0. So it's going to be a short circuit. Now, Hadi, what's the I short circuit?
Now we use the current divider.
Yes, it's going to be 8 divided by 20 multiplied by 15, and this is going to give me 6 amperes. Okay, remember here, I'm trying to find the Norton equivalent circuit. So I'm trying to find the short circuit current that's in parallel with R Thevenin. So what do I need now? Okay. شايفكم زعلتوا انتم. Okay. So what I need now is to find the Thevenin equivalent resistance between A and B. So what should I do? Yasser, back to your question.
Yeah, we need to disable the current source.
How to do that?
We replace it with a short, with an open circuit.
Exactly. So we replace it with an open circuit.
And then we find the R Norton.
Okay, we find the Thevenin resistance between A and B. So what will be the Thevenin resistance between A and B? So we have 2 in series with 8 and in series with 10. So we have 10 plus 8 plus 2. And they are in parallel with the 12. And this is going to give me 7.5 ohm. So then the Norton equivalent circuit is going to be 6 amperes AM. Okay. So you need to practice. because I'm not happy about the participation with the Thevenin equivalent circuits. Everything else was amazing except this part. Okay, now what happens if we have a dependent source? Then if we have a dependent source, finding the Thevenin equivalent circuit will be a little bit more complicated. Finding the Thevenin voltage will be the same. So we still, and the Thevenin voltage and the short circuit current will be the same. But we cannot use this simple method of deactivating all sources and get the Thevenin equivalent resistance. So we need to actually, we are limited to use find the short circuit current, then find the open circuit voltage, find the short circuit current, then take the ratio. So we're limited to that. So we cannot use simply deactivate all sources like we did in the previous two exercises to find the Thevenin resistance. So let's see this with this exercise. So the first thing that you need to ask yourself is, I'm asked to find the Thevenin equivalent circuit. So what will be the ultimate goal? So the ultimate goal is to draw the circuit to find a representation between A and B, something like this. B Thevenin, R Thevenin. This is A, this is B. So finding finding V Thevenin is going to be the same. It doesn't matter whether we have a dependent source or we don't have a dependent source. Finding R Thevenin depends actually on the fact whether we have a dependent source or we don't. So in this case, we have a dependent source. So we cannot just deactivate the voltage, the sources, and find the equivalent resistance. So we need to find the short circuit current. So let's start. Let's tackle this problem step by step. So let's start with the Thevenin voltage. So to find the Thevenin voltage, actually this is one of the easiest question, Yasser.
Yeah, we can. It will be 20i by.
Oh, okay. You're trying to participate.
Yeah.
Okay, خلاص زعلت أنا عليكم. Okay. Yes, you go ahead. It's going to be what?
Minus 25 times 20i.
Minus 25. Oh.
Which is minus 5.
Okay, let's write it this way. It's minus 20i multiplied by 25, which is going to be minus 500i, and this is going to be V Thevenin. All right. So we need to find I. So in order to find I, we need to apply KVL in this loop. So if we apply KVL, what should we get? Ibrahim?
-5. 2000 ohm times I plus 3V.
Plus 3V. We found V to be what?
-5i. 500i.
Okay. So it's going to be 3 multiplied by negative 500i equals to 0. So if we simplify, we will get minus 5 plus 2ki minus 1500i equals to 0. So I will be 10 milliampere. And V Thevenin is going to be minus 500 multiplied by I, which is will end up with minus 5 volts. Okay, now we found V Thevenin. So to find R Thevenin, what should we do? Because here we have a dependent source, so we cannot just simply deactivate the sources. So we need to actually find the short circuit current. And for this circuit, actually finding the short circuit current is actually something very going to simplify our analysis. So if we find the short circuit current, then we need to connect these two terminals together. So notice here what happens if we connect these two terminals. So you'll have a short circuit in parallel with the 25 ohm. So the equivalent resistance will be short circuit, will be 0, صح?
Yes.
So what will be the voltage across the short circuit?
Limited V Thevenin.
Should be 0. So the voltage across the short circuit should be 0 here. So in this case, if the voltage across the short circuit is 0, remember we have a dependent source here. The dependent source here depends on the voltage. So if we have a dependent voltage source with the voltage of 0, it means it acts like a short circuit. So this complicated circuit is replaced with the following. So remember, this one is 0, not because we're deactivating the sources. It's because this one depends on the voltage here. And the voltage here is 0. Okay, so what is the I short circuit current here? So I short circuit current here will be minus 20 I. So what is I? Going back to this loop, I will be 5 divided by 20K or 2K, and this is going to give you 2.5 milliampere. So now I found the short circuit current. I short circuit current will be minus 20 multiplied by I, which is minus 50 milliampere. So R Thevenin will be V Thevenin divided by I short circuit. So V Thevenin was 5 volt. I short circuit is minus 50 milliampere. So R Thevenin will be 100 ohm. So R should be positive here. I went 2 minutes ahead of time. Went 2 minutes over time. So sorry about that, but you can leave if you want. I just want to finish this part and we'll stop. So now we're done. We need to draw the circuit. So this one is negative 5 volt. This one is 100 ohm. AB. Or if you want to write it this way, you can change the polarity of the voltage. Keep it 5. Okay, that's it for today. Inshallah, next lecture we're going to have a quiz, and then we'll continue solving exercises on Thevenin and Norton equivalent circuit. Thank you very much.
دكتور.
Yes.
بعد ساعة تقريبا كذا أقدر أكلمك عشان عندي بعض الأسئلة حق يعني office hours ولا
office hours at 1.
At 1?
At 1 to 1:40.
Okay.
You can call me from 1 to 1:45.
Okay.
Karim?
Yes.
Question?
Yes. How did you get the minus 5 volt? Yes, I don't understand.
Okay. So did you follow the? Did you follow the
Yes,
Do you
I
agree?
know.
Okay,
Yes,
do
I
you
know you
agree?
got the short. Yes, I get this one, and I
Okay.
get the short circuit to get, and I know why we get a 0 on the dependent source because the one that depends on is 0.
Are you talking about this one?
I mean the one above it.
This one?
Yes.
So this is the Thevenin equivalent circuit. So V Thevenin, R Thevenin. So we found V Thevenin to be minus 5 volt. And we just draw it here.
Okay. Oh, I just calculated it wrong. Okay, thank you.
Okay, another question? طيب, okay, we'll see you inshallah tomorrow. Good luck.